So what I'm writing in blue here is what I forgot from from last time. I forgot this here. Right, the kind of actually no, maybe let's just erase that and do this math again. Quicker way of erasing. It's only this last part that has a mistake in it. So I'm going to follow the same thing I did here just to make sure I don't mess it up. So what this equation here, I wrote it differently in my notes. I multiplied both sides by a squared. So that, got rid of the things in the denominator and made this, factoring out the d, ka cosine of ka minus sine of ka. That's the left-hand side. And of course, the right-hand side will be b times 1 minus kappa a oh, I have a sign difference in my work here. When I take this is the first boundary condition, so I had d is equal to, well, where's my second boundary condition? Oh, this lower one is my second boundary condition. One of these should be plus and one of these should be minus. I'm kind of wondering if I made a mistake here, because I have minus signs on both terms here, and it should only be on one term, right? Yeah. So maybe I didn't make a mistake yesterday. I made a mistake in my solution. Not sure how that would work. Anyway, I probably made a mistake and then I made it again. It's probably, it's the way it works. So these are kappas in green, k's in blue. And then using, what substitution did I use here? Well, I just divide all terms by d cosine. What?
Why cosine?
What was that?
Why cosine instead of sine?
Because I wanted to get tangent, actually. And so now these d's cancel, and I have ka minus ka minus tangent of ka and sorry, I got some of my teeth here. And so now taking this and letting d equal b e to the minus kappa a over sine kappa or ka, I have to write down below. then this right side, it's a good thing I left extra space for it. I'll have to resave this. I think I already uploaded once. I have to upload it again. But now we can see that the B's are going to cancel here. The E minus kappa A is going to cancel there. And this here, because this is 1 over sine, these two things here are going to give me a tangent, Ka. So what I have is Ka minus tangent of Ka is equal to 1 minus kappa A tangent Ka. So now I just combine the tangent terms on one side. So Ka equals, actually it looks like I didn't make a mistake, huh? It's the same thing. Just now I have the sine and cosine reversed. So that's our transcendental equation. And I'm trying to think of what I did in my solution. Yeah, my solution has a little bit of an error if I did this right both times, which I think I did. But now with this transcendental equation, you solve for what K and kappa are in terms of each other. So you can like define one variable as Ka and plot them.
Do you care which values of Z0 we need to use? Because I know we need to prove that it can't be less than, that V0 can't be less than a certain number, which I did. But there's infinite numbers of Z0, and they can give you infinite numbers of Einsteins. How big they are.
I will have to look at this further. I only looked at this and said, oh, it was different. But like I said, it's the difference in the minus sign is the entire difference. But it makes a term disappear here and makes life easier if you don't have it.
Yeah.
So I will have to look at it again to be clear on exactly what my solution is. Yeah, I think that's all I showed is that you had to have that limit, like you said. So yeah, I'm gonna have to redo this stupid sign error. Good thing you got that on the recording, huh?
Yeah.
Next time, let's not start the recording until I get past that. Okay, we're gonna do, I don't know, something I find easier. We're gonna deal with some operators now acting on our solutions that we have found. And I don't know that we're actually going to have them act on the solutions today, but we're going to get that direction. So first, this is just, we're working on operators in spherical coordinates. And so the position operator is, r hat, if you will. The hat now not meaning unit vector, but the operator. And we could put the x operator in terms of r, theta, and phi if we had the hankering. So we looked at this yesterday when we looked at orbitron. If we want to find the probability of the electron being r distance away from the nucleus, we can't just take psi mod squared, dr. That's not going to be the probability because it's a three-dimensional problem and I was looking at it one-dimensionally. We have to put dv. And so the probability of being at radius r dv is going to be, and here I have dv for spherical coordinates is r squared sine theta dr d theta d phi. And so if we want to find just the r portion, we have to integrate out the theta and phi parts. And so if you take the psi and you integrate out the theta and phi parts, well, you've got this integral that you have to do, and then r squared dr. So it's a little more complicated, right? And so that's why things look different when we were looking at Orbitron, the radial solution versus the probability finding at some radius r. Expectation values, it's the same method as before, but dv again is going to be having this stuff. So there's my dv underlined in brown, and then I have psi star, the operator, and psi. So if you want to find the expectation value of, for instance, energy, you're going to have this stuff, and then your psi, your Hamiltonian operator, psi. Well, this is psi star. That's psi. And then you've got to do that probably more sophisticated integral, which I hope to never do.
Can you go back?
So as you saw for the title for today, I said angular momentum operators. So angular momentum, we have to back up to our basic physics just to make sure we understand angular momentum is the rotational analog to linear momentum. So angular momentum is inertia for rotation. And so sometimes we'll talk about the moment of inertia, sometimes we'll talk about the rotational inertia, same thing. If you are sitting in your chair and spinning, you'll keep spinning unless there is a torque acting against you to slow you down or speed you up. And so these chairs have pretty low torque for rotation about a vertical axis. So if you spin about a vertical axis, now when I say spin about a vertical axis, what direction do you spin? You're spinning like this.
Yeah.
Right, because you're spinning about this axis. And what we call that then, if we call the vertical axis z, then this is angular momentum in the z direction, spinning about the. Dang! My knee just did something bad. So I was trying to spin. Ouch.
Okay.
Probably?
I thought you just got dizzy.
No. I'm going to sit down now. I should have been sitting and spinning instead of standing and spinning, right? Less chance of injury. Speaking of hospitals, I got an email from Dr. Seth today.
Oh, that she had her baby?
He said he won't be in for class this afternoon because they're having a baby today.
Yeah, they induced this one.
Yeah, so should be a baby today. And my knee should be okay, baby. Guess I'm not going to the gym this afternoon. I can't believe that. All right, so the point I was trying to make before my knee gave out was that angular momentum in the z direction means a rotation about the z-axis. Angular momentum then, if we define that's x and that's y, what direction would rotation have to be? This is x here. So angular momentum in the x direction, what direction would the rotation be? Yeah, it'd be going like this. Okay. And for everyone listening on YouTube, hey, sorry. At least you didn't have to see me hurt my knee by standing and spinning in a circle. So here is the actual calculation that we use for angular momentum. Angular momentum, oftentimes in general physics, we just put I omega, right? But it's also equal to R cross P. The two are going to calculate the same thing, but they're useful in different ways. If I have a ball coming toward a batter, the ball's not coming straight at the batter, right? It's coming toward, it's not supposed to. It's supposed to be coming out here, hopefully in the strike zone, And so that ball not coming straight at the batter means that there's a certain angular momentum that you can calculate for the ball about the batter. So using that as an example, here's my batter. He's a dot. Here's the ball. And so if we want to find the angular momentum, we're going to take R cross P. So at some instant, let's say the ball is here at some instant, then the r vector is the vector that goes like that, and the p vector is going like that. What does it mean to do r cross p? What does a cross product mean? The perpendicular components. So if we take this, we could say, well, the r vector, the perpendicular part of the r vector is this, right? And that's going to remain the same. Even as r changes, the perpendicular part is going to remain the same, assuming the ball is not tailing away or curving into the batter. And the momentum stays the same. And so the angular momentum stays the same as the ball is coming toward the batter in those conditions. But it's something that we can calculate, and we certainly could not have used the upper equation to calculate that angular momentum, because that's specifically for an object of moment inertia I rotating about a fixed axis. This wasn't that case. So we're going to talk about this. It's important to see the difference, because when you have an electron orbiting the nucleus, we don't know what the radius is, right? We don't know what the path is. So the idea of I omega doesn't quite work out, because if we don't know what the path is, right? I omega would work if it was doing a circle, but if we don't know the path, that's not going to work. But with the other direction or definition, it still works. So this is the one we have to work with. And this is the general way of doing a cross product. To do a cross product, if I want to do A vector cross B vector, I put the unit vectors, so I'm going to put E sub x for a unit vector in the x direction, E sub y for a unit vector in the y direction, E sub z for a unit vector in the z direction. Then I put ax, bx, oh, whoops, that's not an A, and that's not a y. Ay, az, bx, by, bz. Order is an important thing. I have to make sure the A's are in the second row, the B's are in the third row, A's being the first one in my cross product, B's being the second one. If you reverse which row they're in, you get the opposite direction. And then if I'm going to find that, I'm going to say, well, A cross B, and I think we've gone over this previously, how to do determinants. We did when we were talking about finding the eigenvalue for a matrix. And so this time you have to take this row. If you don't take that row, you're going to make life a lot harder. I say you have to. You don't have to, but you're going to make life harder if you don't. So I take the first one, E sub x, and multiply it by the determinant of its co-matrix. And then I do minus the second one, EY. As I said, technically you can write this out as one thing with the Levi-Civita symbol, but we're not doing that. It's determinant of its co-matrix. And the co-matrix is found by taking the row and column that I'm in and removing them. So for instance, for the second one, I took out that row, or that column and that row. That's how I got the co-matrix for the second one. For the first one, I had taken out that row, or that column. Wow, I'm good at this. And so for the third one, I'll take out this column, change the sign again, plus EZ, AX, AY, BX, BY. So that's generic. That's not what I want to do here. I want to do specific. And so I have the determinant written out here that I'm going to actually do. So using exactly the same ideas, EX, EY, EZ, RX. What do we usually call RX? The radius in the X direction. We usually just put X. And likewise, RY will be Y, RZ will be Z. And then PX, what is PX? H bar over I. Remember our operators? d dx, right? H bar over I d dy, H bar over I d dz. So there I've put those in explicitly. Now, if you look up above, I did not put them in explicitly. The reason I put them in explicitly is, well, it becomes clear that order matters when you have a derivative. It's not so clear when you have x and px that order matters. But when you have x and h bar over I d dx, it's clear that order matters. We've already talked about commutators, and you know that's not going to be the same as if you reverse it. So now when you do this, you have that. And now another rule for the determinants that's important. Order matters. You have to do your determinant in this fashion. This minus that. So the y is going to become before the h bar over I d dz. The z is going to come before the h bar over I d dy. And if I hide that, I can do the last one, I think. So there we have the angular momentum vector, the operator. And so the one in red, take away the unit vector, and we would call that the angular momentum in the x direction operator. Take away the unit vector, and the next one, including the minus sign, is angular momentum in the y direction operator. And the last one, the green, is angular momentum in the z direction. So what's written up here is the same thing except for the p, I wrote pz instead of h bar over I d dz. And likewise, py and px. So one other thing you probably notice is different is the order. I put the positive first in ly. So down here in ly, the positive one is going to be minus a minus plus z h bar over I d dx. And so I put that one first here, just so I would have positive mine and then a negative for all of them. So these are how we find the angular momenta components. So that's mathematical. Do you have questions about that math? Okay. It depends on what you're doing. If you're doing the calculation, then you write it out. If you are before the part where you have to actually do the calculation, you write the P because it's shorter. Okay, so now let's find some commutator relations. The the next slide will say, as on our previous slide, and of course we haven't done any yet, the commutator relations between angle and momentum give us important information. What specific information do we know if they commute? What about if they do not commute? So what do we know if they commute? If operator A and operator B commute, what's important about that? Exactly. You can know them both simultaneously. If not, then you can't. So let's find them. So first of all, let's find LX, LY. And this is something we can do without doing derivatives, if I remember correctly. So what is LX? Well, from our previous slide, that's going to be Y PZ minus ZPY, right? And LY is going to be ZPX minus XPZ. So with that, we just go ahead and write it out long form. YPZ minus ZPY, what I like to think is zippy, times ZPX minus XPZ minus, change colors for the minus, ZPX minus XPZ, YPZ minus ZPY. And of course, already this is becoming annoying, isn't it? But we're not even halfway in. It's good to know. So now, multiplying through YPZ ZPX minus YPZ XPZ minus ZPY ZPX plus Z, why did that Z come out wrong? ZPY XPZ. That's what was green in the first one. And now we have to subtract ZPX YPZ minus ZPX ZPY minus XPZ YPZ plus XPZ ZPY. Feeling good? We're now past the hump. Now we have to simplify. So let's simplify. YPZ-ZPX. Which ones can move past each other and which ones cannot? Well, it actually comes back to commutators. What can you tell me about the commutators? We've already done x comma px. What's x comma px equal to? Front cover of the textbook. I think it's IH bar. Do check. Don't take my word for it. Yeah, front cover. Should be. Okay, so XPX is IH bar. And what is XPY?
Didn't we say that was 0?
Right. So XPY being 0 means I can freely move X and PY past each other. But XPX being IH bar means I can't just freely move them past each other. Because if it's equal to 0, that means there is no difference if I flip the order. But if it's not, then it's going to make a difference. So I'm going to rearrange things by putting the things that have a fixed order together and the things that don't in front of them. And so this first one, YPZ-ZPX, there are two things that have a fixed order there. Which are those two? I didn't do the P's here. I guess I should do PX comma PX. What's PX comma PX by definition? Yeah, 0 because it shouldn't matter. And what about px comma py? One's derivative with respect to x, one's derivative with respect to y. 0. So that means I can freely move all p's around with other p's. But I can't move a px across an x or a py across a y or a pz across a z. So I'll put my distance variables first and then my momenta. And then the ones that I can't change, I'll put in parentheses. The next one, what do we have there? Everything can move past the others. So I'm going to have xy pz squared. The next one, what do we have here? Yes, that's right. And the last one? Okay, the z and the pz can't move across each other. And then going to the black, now I'm going to bring the minus sign in as I'm doing each individual one. So I have z px y pz. The z and pz can't move across each other, so I'm going to have minus y px z pz. The next one, z px z py, all of those can move. The next one, x pz y pz, again they can all move. And the last one, have that. I don't know how many of these I want to do. I'm probably going to stop at 1. You see, you can see a good reason to stop at 1, right? So now we have to look at, can we subtract anything out? We have z squared px py and minus z squared px py. Those subtract out to 0. And we have minus xy pz squared and plus xy pz squared. Those also add out to 0. And then we have ypx and xpy with things that are order specific. So now I can write this out as so there's my stuff with ypx. And xpy has now, of course, if you look at these, this here and this here, they're the same thing but in opposite order. And what is zpz minus pzz? So that's IH bar. And so what does that make this here? Yes. So I'm just writing out what we have. And then rearranging that, we have IH bar times XPY minus YPX. That's an X. Doesn't look like it, but it is. But what is XPY minus YPX? XPY minus YPX is LZ. Woohoo! So what we found is LXLY commutator is equal to IH bar LZ. It took a fair amount of work, didn't it? If I were to do LYLZ, what do you suppose I would get? Yes. If we change it keeping the same order, we'll get the same outcome. So as long as I go XYZ, I could go, YZ will give me X, ZX will give me Y. And of course, if you change the order, it just changes the sign. So we can stop here. We've done one fully, and we understand how it's going to shift over. So here are the three solutions from our previous page. Of course, we only did the first one. The other two we intuited. So that's something useful. What does that tell you, though? What does this tell you? What does it mean? That's an A, than one component of the angular momentum. Well, that's a little disappointing. A little disappointing that you can't simultaneously know LX, LY, and LZ. But, the math is clear. It's not ambiguous. You can't know them at the same time. Now we're going to introduce something new. We are going to start off by saying Z is our sacred direction. If I put something in a magnetic field, then the direction of the magnetic field I'm going to define as the Z direction. And the Z direction is the component I'm going to choose to know. And so the X and Y directions, the ones I won't know. And so you can see this looks exactly like the ladder operators we made before. Well, exactly like in that we have a plus and minus out front. And notice this is just two equations. When you have plus or minus, you read the tops together or the bottoms together. So this is L plus equals LX plus ILY, and L minus equals LX minus ILY. So those two equations are what the one is telling us. So we're going to introduce these commutators. And now it says, check its commutator relations. You excited? It's not as hard because we've already done the hard one. So if I want to do, for instance, LX, comma L plus, it's that, right? Just substituting for L plus. And so multiplying that out, I didn't need the parenthesis on that. Try to keep my colors a little coordinated. Remember, order matters. You can't just rearrange things. Otherwise, the commutators have to be 0 to rearrange it. So if we look at this, what's the first thing that just pops out at you? Yeah, the LX squared subtract out. And so we're left with equals I Lxy minus Lyx. But Lxy minus Lyx is the commutator between Lx and Ly. Sometimes my hand just doesn't keep up with my brain. So I dropped two L's in there. So what is Lx Ly, the commutator thereof? So that commutator Lx with L plus is minus H bar Lz. Right? That wasn't nearly as hard, was it? It's kind of good to have that. So that was Lx with L plus. What if I did Ly with L plus? What do you suppose I'd get? Going to actually do it out because it's not quite as intuitive, I don't think. You very well could have been right, but I don't think it's quite as intuitive, so I'm doing it out. And just like last time, we have this here that subtracts out. Ly Lx minus Lx Ly is equal to minus Lx Ly. And so that's going to be minus I H bar Lz. Yes, I believe that's right. So the Lx and the Ly, there's their commutator relations. A little bit different, right? There was no I in the one with Lx, but there was in the one with Ly. And if I'd done L minus, what would have been different? The difference in the L plus and the L minus is changing the sign of the term with the imaginary number.
So your answer is the opposite side.
So since these had the I with them, it would change the sign. So Lx with L minus would be minus this, so plus H bar Lz. And here, it wouldn't make any difference because the terms with the i's were the ones that subtracted out. Finally, and I left myself enough space for this, hot tip. What if I did Lz, comma, L plus? Now nothing subtracts out. Maybe I didn't leave myself enough room. So it's 8 LZLX plus I LZLY. What is LZLX? And then plus I times LZLY, which is minus IH bar LX. And so the last one's going to be plus without an I. So here is, oh no, I didn't. Hey, those we already did. Yeah, okay. This here is written in an obscure fashion, but it is what we found there. Notice that it has L plus minus, and it was in reverse order, but so it has the two terms, the LX and the LY in the solution, the LX and the LY. One of them's real, one of them's imaginary, and it's got the H bar, the extra H bar there.
So that L just stands for the LY plus the LX component, for the ILY plus LX?
Run that by me again.
The L in that answer just stands for the ILY plus LX.
This L here, yes, that's L plus or L minus. So it's LX plus or minus ILY. And if it's the plus, then it's the plus. Minus, that's the minus. Now, what we did not do is we didn't do the L squared commutators. And so we probably should do that. So what is L squared? Also written as L dot L. If I do a dot product, what am I multiplying together? That's cross. Cross is perpendicular because of the cross. So it's the parallel part, so that means it's LX squared plus LY squared plus LZ squared. So if I do the commutator between L squared and LX, that's going to be so expanding that out, LX cubed plus LY squared LX plus LZ squared LX minus LX cubed minus LX LY squared minus LX LZ squared. And what's the one thing that jumps out to make it somewhat easier? The LX cubes subtract out. So we have these relationships left. And so using our commutator relation, I can rewrite I'm not going to do, oh, I'm out of time. If I change the order of a pair of these, for instance, if I change the order of these two using a commutator relation, then I could have LY at the beginning of both of them. And so this first term I could write as better be careful here. I don't remember if it's plus or minus at this point. It's either plus or minus. LX, LY was IH, LZ, right? You can factor it like that. And then you have a commutator here. And you do the same for the second part. We're totally out of time, so I can't finish it here.
So for the rest of the semester, I'm wondering what the schedule looks like, because according to the syllabus,